Welcome, everybody. This is our webinar series on the supercomputing spotlights, and I'm really excited to have Mike Haru here. Mike is a senior scientist at Sandia National Lab. He's the former director of software technology for the US Department of Energy Exascale Computing Project, or short ECP, and he's also a scientist in residence at St. John's University in Minnesota. His research interests include all scalable scientific and engineering software aspects for new and emerging parallel computing architectures, and he has done a lot of works over the year in these areas. So he's also founder of a variety of very well-known software packages like Trilinos, Cocos, Montivo, and the HPCG benchmark. He also leads the extreme scale scientific software stack, the E4S project in DOE. And he is the PI of the PESO Software Ecosystem Stewardship and Advancement Project that focuses on post-ECP scientific software efforts. He is also a fellow of the Society of SIAM, of the Society for Industrial and Applied Math. He's a distinguished member of the Association for Computing Machinery, ACM, and a senior member of IEEE. He serves on the ACM publication boards and is chair of the ACM New Publications Committee. And I'm really excited that he's here now to tell us all about all in on GPUs from desktop to exascale. So thank you.
All right. Thank you very much for the introduction, Ulrika. Yeah, so let's get started. So maybe just a little bit of background. I think if you went to Lori Deishin gave a presentation a month or two ago and talked about the Exascale Computing Project, or ECP. That's an acronym I'll use fairly often. From her overall director role, and I'll use a little bit of content just to make sure we're all kind of have a context for what we're doing. So ECP was a 7-year project, $1.8 billion project. When a group of people receives that much money, there's a fair bit of oversight associated with it. We were actually managed as a tailored construction project, which was the kind of framework that we used for managing our activities. And overall, I think we learned a lot about how to conduct such a project. There are discussions for the future of how similar large projects can be managed, and the lessons learned from ECP are going into that conversation. So we had 3 focus areas. One was the application development, software technology, which you'll hear a bit about today. That was the one that I led along with Lois McInnes, and then hardware and integration. These were the 3 areas. It was a big, ambitious project. We developed a lot of new algorithms and software, got them into the hands of the users that needed them, and it provided a lot of reusable infrastructure along the way that we will continue to sustain and advance as we go forward. ECP applications came in this collection of categories. And I won't go through these in detail, but you can see that the main thing I want you to take away from this slide is the breadth of application areas, and within each area, the kinds of applications that were created. This is truly a holistic effort. The machines that were built for the Exascale project and beyond, where, as DOE likes to say, we're in the Exascale era. These machines were not built as stunt systems. They were built with science and scientific progress in mind because of the collection of applications that are covered in this space. And so we had 62 different applications, over 10 million lines of code. Some had large communities, others were smaller but really important. Most of the code team started with just MPI or MPI plus some modest OpenMP on CPUs. But by the end of the project, all codes went through this transition from, say, the many-core CPU to CPU plus GPU to CPU plus multi-GPU, then GPU resident, and then diverse multi-GPU, and then with some architecture-specific optimizations. And so by the end of ECP, all of these codes were being able to utilize the GPU-based exascale systems, and all the way from the desktop up of those systems. Because one of the really unique things about exascale as a milestone is that it was fundamentally about having good GPU performance and then scaling across many GPUs. But this, GPU resident performance was a really important aspect of what we're trying to do. And that's, of course, true for any system, whether it's a supercomputer with thousands of nodes and many GPUs, or a single system with one GPU. And all of that work can be leveraged all the way from the desktop on up. Part of that effort was the creation of reusable libraries and tools, and that was the area that I led. We had 70 different software products, and I'll talk about a few of those today. And they were used by the application teams and by the computer system vendors and by the exascale platforms themselves. We cover a broad range of user types, but they played a critical role in the performance and robustness of the applications. And I'm showing these kind of tiles of the applications. So many of the applications had a figure of merit speed up that they had to achieve. And it wasn't just simply performance improvement. It was often a scaled science improvement capability. But if you look at those FOMs, FOMs, you can see 300, almost 400, 70. They had to do 50 or better. 270, 500, 3,500 almost. And this was the kind of experience these teams were having as they were getting onto and porting their codes to these exascale platforms. This is truly transformative in terms of the science that is able to be computed and results for and advances in scientific computing. And that's why calling this the exascale era is not really an overstatement. We truly have results that merit that kind of high profile statement. We targeted 3 specific systems: the Frontier platform at Oak Ridge, which is an AMD GPU based system, an Intel based system, Aurora, at Argonne, and then one that is almost ready, the El Capitan system at Lawrence Livermore, also based on AMD, but with advances in the GPU and the system design, and based in part by what was learned from Frontier, but also based on that advances that vendors have been making in between the delivery of Frontier and El Capitan. So let's talk a little bit about the impact of ECP, the libraries and tools efforts in particular. We had 6 technical areas that were underneath the software technology portfolio. The first 5 were functional in their organization: programming models and runtimes. So development tools was second, math libraries was next, data and viz, and then software ecosystem. The 6th area, the NNSAST, was projects that were funded by the 3 labs, Sandia, Los Alamos, and Lawrence Livermore, but we're producing open source capabilities. And so those all filtered back into the other 5 areas and represented some really important contributions. For example, Spack and Cocos were 2 things that grew out of the NNSA portfolio and then became really important to the broader community. So anyway, this was the organization of the projects under the software technology area. And I'm going to go through some examples from the first 5, recognizing that many of them are actually from the NNSA software technology portfolio. So here's a sample. So programming models and runtimes. Generally speaking, teams, our mission was to have performance portability across the target architectures. That meant that you can't just write CUDA code. You can't just write HIP or SYCL, which were the 3 vendor programming models. You had to in some way support all 3 of them. Some of them did GPU-specific kernels. They isolated their performance-sensitive code to specific kernels and then had distinct versions for each of the target architectures. That can be a good approach. Others relied on loop-pragma models. This was particularly true for Fortran codes. Some people use co-design frameworks. For example, Amrex was a very popular co-design framework. And Amrex adaptive mesh refinement suite had its own way of managing the underlying various architectures. And then a lot of people use C++ abstractions, and I'll talk a bit more about that. They use Cocos and Raja, both developed by the NNSA labs. And I'm going to talk specifically about Cocos. It's the one I know best. It's also the one that has broader penetration in the science community and has some really nice ways that you can bootstrap if you want to try to use Cocos. And even if you don't end up using Cocos, the concepts, the principles that go into Cocos are foundational for any kind of effort that you want to put forward in having node parallel programming capabilities. So these are the steps that went into a lot of efforts, kind of a general way. You port the code, you rewrite profile optimized. Memory coalescing was important for memory system performance. Loop ordering was something you had to pay attention to make sure you could provide enough concurrent execution. These devices are multi-tera-op devices, and so you need lots of work that can be done at a time in order to get most of the performance from these GPUs. And then kernel flattening, a technique that allowed you to have more work, again, concurrency available for the GPUs. In addition to that, you often had to reduce synchronizations. Latency is a huge performance killer on these platforms. And so limiting or eliminating synchronization, which in a sense forces halting or waiting for data, had to be reduced in some ways. Getting rid of it or hiding it with other computations was really important. Reduce precision. Most of these devices, and I'll talk about this a bit as we go along, have reduced precision, not because the scientific computing community needs it, but because the AI community needs it. In fact, we call these things GPUs, but really they're nowadays AI devices. The graphics part of it is in service of AI. And then communication avoiding, I mentioned a little bit. And then adapting models, looking for different mathematical representations, looking for the ability to recompute something versus looking it up in some kind of array or table. And then looking at new physical models. So all of these techniques were used within the Exascale project to achieve these 100x or more types of performance improvements. What's really nice about all of this is because of the broad set of applications and the success of these application teams, ECP's efforts are a signal to other people who want to embark on this disruptive change to your codes. Moving away from CPUs is really hard. Introducing parallelism underneath MPI is really hard. It's nice to have some success stories that, first of all, say it's possible, but then also provide some kind of path that you might follow. It's not unlike, if I'm not a climber, but I read stories, climbing El Capitan, different El Capitan, not the machine, but the mountain. As teams discover paths to climb, really difficult mountains, once a team figures out how to do it, once a climber figures out how to do that, and it may take months to figure that out, other teams can follow quickly because they saw how that person did it or how that team did it, a path that they took. I think a similar dynamic is at play with what the Exascale project did for use of GPUs and scalable computing on GPUs. Okay, I also want to talk a little bit then about, what is the distribution of the parallel models? This shows, this is one snapshot based on some surveys that we did. And it shows that all of the different approaches that I mentioned earlier. And it also shows that, the Cocos-based approach is widely used. And that's part of why I want to focus on that one. Raja has a lot of similar characteristics. It actually has some really nice features to it that, they took different design approaches than Cocos that are really attractive. And so I don't want to disparage Raja. It's a great product, but I think in terms of accessibility, Cocos offers some really nice outreach possibilities. So let's talk a little bit about the Cocos programming model. What is Cocos? It's a C++ programming model for performance portability. It's implemented as a template library. So it uses what's called C++ template metaprogramming that allows you to write code in a way that is generic in a certain way and that doesn't have CUDA, or OpenMP or HIP or SYCL in your source code. Instead, there are backends that when you compile Cocos for a particular target platform, that's the vendor specific or the program specific code gets blended in at compilation. And so it allows you to have adaptable code that at compile time becomes very device specific. And so now compile times are big, in a lot of instances. And so, there's cost associated with it, but it doesn't come at the programmer's portability cost or at the performance cost. It comes in the compilation. There are lots of library systems that have been built out of Cocos capabilities, a lot of institutions, and also worth noting, it's not just for GPUs. It also supports CPUs and vectorization on CPUs, which is an important form of concurrency. So this is just a dynamic or a kind of a sketch that shows the different kinds of applications, different platforms that are supported by Cocos, and gives you a sense of the kind of breadth of what the activities are about. And then this is the ecosystem that's been built up around Cocos. You can see that there's the tools, there are debugging, profile, and tuning tools, lots of documentation and tutorials, lots of kernels. Cocos kernels is a separate package. The math libraries, in particular codes like Trilinos and PETSI, ArborX, Cabana, have all provided their users the ability to use the solvers and other advanced algorithms in their library by utilizing Cocos arrays and data structures and functions. And so if you invest in Cocos, you get access to the use of these other libraries as a result. And then a whole bunch of other capabilities that I think are really nice. The fundamental value proposition of Cocos is it abstracts the data structures and the execution of functionality to allow you to express in an abstract way and then compile specifically down to where and layouts and patterns and how. And this is the fundamental value proposition of Cocos, is that compile time these things get resolved, while at the time you write your code, you don't have to specify them. Just to have a very simple example, here's an AXP operation, a vector update. In Cocos, you would provide the parallel 4 pattern. You'd give it a name for profiling debugging. This is the execution policy. This is how you would handle the indexing. And then this is the lambda expression or the loop body. Sometimes you use what's called a functor to do that. And so just a little bit of how that works. I mentioned the Cocos support, lots of different lectures. There's online, pre-recorded, and exercises that go with that. And then there's also now a new effort for BLAS and LAPACK type functionality, if you're familiar with those libraries for dense linear algebra. Okay, so that's a little bit about programming models and runtimes. In the development tools area, again, there are lots of nice libraries. I'm going to show you one called Variorum. It won an R&D 100 award in 2023. And this is a theme of a lot of the tools areas, is that vendors have specific ways of managing power, energy, frequency, thermals, and performance counters, but they all do it a little bit differently. And so what Variorum does is it provides a single API with access to that pays attention to the different types of users that would want to get that kind of information and manage the system at that level. And so it's a very nice package. The team that put that together has also put in a lot of effort to make sure it works with all of the other tools that make sense in the ecosystem. So that's the development tools. In the math libraries, again, lots of really nice capabilities. I highlight this one. This is an effort to support systems engineering, where you formulate a symmetric indefinite system, and it doesn't have supernodes. So it's you can't use a typical supernodal solver and get performance out of it. But combining some technology from the SuperLU code team, the Ginkgo code team, and then leveraging the domain expertise of the Exa SGD team, which was one of the application-oriented teams. This solver that is part of Ginkgo is a performance portable solver available in a portable way, performance portable way on any GPU, and it competes really well with vendor-specific capabilities. So this is in this math library space an example. In the data and visualization space, again, lots of capabilities, I/O tools and libraries. I highlight the ZFP library, which uses data compression to reduce the actual system requirements for data that you need to store and move. By compressing the data, either in a lossy or lossless way, you can reduce the actual amount of data storage and movement that's required, and you get diminish the impact of our ever increasing ratio. Our compute performance generation to generation gets faster relatively than our I/O performance. And so libraries that do data compression allow us to reduce the impact of that growing disparity between compute and data movement. And there's many more. ECP generated lots of, as I said, there are 70 different libraries and tools that we tracked, and there were others that that came along with that. And these are GPU capable libraries, even at the desktop, for AMD, Intel, and NVIDIA GPUs, and also for vectorizing CPUs, ARM, and increasingly Intel and AMD CPUs. And so we're also tuned to be able to take advantage of next generation high concurrency node architectures. We already have a starting point, for example, for data flow devices, where you have a network of lightweight compute cores that communicate with each other and data gets transferred between them in a very lightweight fashion. And we're already, partway prepared for those kinds of devices. And the result of that is this collection of software. And I put in a few example products that we supported a couple different MPIs. We supported OpenMP and OpenACC. I mentioned Cocos and Raja. We supported work in LLVM, injecting HPC features into the LLVM compiler suite. Performance tools, PAPI, Tau, HPC Toolkit, the math libraries, I/O, and data and viz. And so the result of all of this is a stack that enables performance portability on leadership platforms and all the way down to the desktop. I want to mention a little bit about Spack. Spack is how we build and test our software. Spack is a product that was created before ECP started, but it was relatively new when ECP started. And so it's something that grew in capability and robustness and adoption as the Exascale project also grew. It's a wonderful a way of supporting the use of your software and the software you depend on. You create recipes, and I won't show you recipes, but this is Spack install MPI leaks, a particular library that people like to use. And so you can simply say Spack install MPI leaks. There is a recipe sitting out in the Spack ecosystem that knows how to build that and knows how to build all the dependencies of MPI leaks. And so it will build not just MPI leaks, but everything that it depends upon. You can short circuit that if you have existing builds of some of them. But it does the installation. Also, you can decide specifically which version if you want. And you can say which compiler it should use. You can turn on various features. You can give various flags to it. And so there's a lot of adaptability, and all of these installations can coexist in the same file system. And so you don't have to just install one. There's also build caches of signatures that you can create and squirrel away copies of builds, binaries that have been built. And then anytime a new version of that library needs to be built again, you can go grab that binary and stick it in and greatly reduce your build times. In fact, we saw by a factor of 10 or on average for that kind of rebuild cost savings. E4S, we said there's 140 currently. You're not meant to be able to read this, but you can see how using Spack and then the recipes that we associate with Spack, we can build this entire stack with regularity, robustly, and with performant configurations. And we do it on lots and lots of systems. And just a little bit about the growth of Spack. So this was back in 2016, about the time ECP was getting started. And then 2018, you can see the growth. Fall, more growth. 2020, 2021, 2021 again later, 23, and now in 24, and even this is a bit old. And what I want you to see is look at the green box in the upper left. And this is how it's represented in this larger box. And so you've seen there's been tremendous growth in every dimension with Spack. So it's a very robust and exciting capability. And we use it with E4S as we go forward. And all of the libraries and tools that are in this ecosystem also use Spack. So I'll mention the Extreme Scale Scientific Software Stack. This is one of the big legacies of ECP. Excuse me, in the software technology area. We provide a lot of value add to the libraries and tools that are part of E4S. So certainly those tools are why you would want to use E4S, but we also provide community policies for improved commitment to software quality. We have a documentation portal that allows you to search for and sort the various libraries and tools that are part of E4S. We do a lot of portfolio testing, especially on leadership platforms. We curate, so every release, we make sure that at least with the smoke tests, that there's no gotchas in the build of all these different versions of the libraries that are part of a E4S release. We do regular releases. I mentioned the build caches. We have a strategy for going forward. You can go grab all of this from e4s.io. And we're increasingly seeing that by providing this ecosystem, we can improve the value proposition of the libraries and tools that we work on to the broader community. This is just a little case study so we worked with DoD as part of the Exascale project on our industry and agency council. Sean Ziegler, who works with them, did his independent study in the use of Spack and eForest without DOE's assistance, and did it in 2 phases. And here are some of the highlights from that. He installed Flux. It's the first time. Flux is a really nice scheduler for launching by the user and managing a set of nodes, a task assigned to the user. They were able to install it easily and for the first time be able to give this to their users. Tau, they use it a lot, performance analysis tool. Again, very easy to build under E4S using Spack. Cocos and Raja, they had used a little bit of Cocos with LAMPS, molecular dynamics code, but they were able to do a turnkey installation of both of them and run them both on GPUs and see performance improvement. Again, very turnkey. And then LAMPS, although they already install it, they tried it through Spack and E4S, the E4S recipe for LAMPS. And the really cool thing about that is even though they've been using LAMPS for a long time, the recipe that they got through the E4S specification actually built a version of Spack that's 2 times faster in execution than what they were able to do on their own. And so not only did it build it, but the version of the build that it created was twice as fast for solving their problems. So that's some of the value proposition we see in this space. We do regular releases. We did one in May. There will be a new one in just prior to supercomputing. And I'm not going to go through in detail. This is a lot of the capabilities that are there. It's a very rich software ecosystem, not only for HPC, but also for AI. We actually pay a lot of attention to the AI libraries that are being developed for scientific applications and include those as they become available and people have interest in them. Okay, so let's look a little bit forward to post-ECP software stewardship and advancement. So there are 8 software stewardship organizations, we call them SSOs, that DOE, Office of Advanced Scientific Computing Research, sponsored starting about a year ago. And these efforts are continuing. I'm the PI for one called PESO, and these are the other 7 of them. Some of them are product-oriented, fast math and rapids focus on math and computer science libraries, respectively. S for PST is on programming systems. STEP is for performance tools. Collabs and Corsa and SWAS as workflows. Collabs and Corsa focus more on community-oriented aspects of the ecosystem. And then Peso provides primarily E4S and Spack advancements for the open science community and other kind of community-oriented activities like the BSSW Fellowship, which if you're interested, has been announced and applications are being accepted. Anyway, so these are some of the kind of goals of CAS. So and CAS brings to these SSOs a kind of governance layer. And it's the Consortium for the Advancement of Scientific Software. Again, some of the basics that bring together these SSOs and have us talk with each other. For example, we had Birds of a Feathers Day in June. All of the teams from the SSOs that wanted to do a BOF, we did that and coordinated it through this CAS infrastructure that's in place. And CAS is meant to be more than just the SSOs that DOE is sponsoring. We're viewing it as a much broader way for people who are interested in producing and using scientific software to go forward. So this is just getting started. We have a bootstrapping process. This is the bootstrapping team. We meet on a regular basis. We're almost done with the bootstrapping process. In the next few weeks, we have a charter, we have bylaws. We're forming a steering committee and forming an external advisory capacity for CAS. And so you'll see some announcements of that, again, probably at SC24. Peso, as I mentioned, is a project that I lead along with Lois McInnes. We provide these two, Spack and E4S and a bunch of other capabilities. I leave this side behind for you to take a look at some of the details. The last thing I want to mention in this space is we recognize through ECP that having a software ecosystem is incredibly valuable. But it's not necessarily what you would notice right away. If you're building all of your own libraries and tools, and you're trying to manage that, you may not see that having a curated ecosystem can help you, but it really can. And so, these challenges, if you have difficulties installing third-party libraries and tools, managing version updates, let's say you want to update the version of one of the libraries using, and then you're finding out that requires updates to a whole bunch of other things that you don't really want to update, but you're required to because the new version of the library you want needs those things updated too. If you want to use a new library or tool, but you don't know how to do it and you don't want to go through that effort, these are all things, right? Managing portability, long build times, the build caches that we provide. If you want to increase the value of the algorithms you want to use, think of a library like Hyper. Ulrika is part of that team. They are working on Hyper, month after month after month, improving it on a regular basis. And so by investing in the use of Hyper, you can get those advances even without your own work, just because they've been doing good work behind the scenes. And these are all ways. And I use this kind of powers of 10 possibility as a way, 100,000 or plus lines of code that you don't have to write. 10,000 community members who are also engaged in this ecosystem that you can leverage from. 1,000 or more code teams that are using the ecosystem. I showed you the speed ups on GPUs, 100x or more. The build times using build caches can transform your workflow. And then the one source code base for all computing system with maybe some variations. I didn't go into how you do that, but if you have hotspots, you can customize code for those hotspots, but still have the majority of your code be a single source base for capabilities. Okay, just a few more slides and then we're done. High Performance Software Foundation is something that got launched at ISC 24. This is a great advance for our community. It shows the market value of HPC and high performance AI and high performance modeling and simulation to the broader I would say, economy, broadly speaking, industry, agencies, universities, anybody who cares about, the use of technical computing sees some value in this high performance software foundation. This foundation will allow us to maximize the cost and benefit sharing of the libraries and tools that we produce. You can see already in the projects, Spack, Cocos, E4S, Trilinos, Aptainer, all of these things, and more are joining the HPSF. And one of the great values is it actually provides money. The annual budget we expect initially is $1 million, and that can be used for enhancing the quality of what we're due to the community, providing workshops, providing tutorials, doing more robust testing of things. And so HPSF is a great advance. Okay. Oh, so the last key topic I want to bring up is this is to you as a community. The growing success of generative AI is spurring disruptive changes in scientific software. GPUs are really AI devices. I mentioned that already. CPUs are still relevant. I don't have time to go into, but one of the really big things I think is true is that Hyperion had a survey saying that the AI market is about 30 times larger this coming fiscal year than traditional HPC. The bad news is we're no longer a strong market driver. We just don't have enough revenue potential. The good news is that we're still a big market, but AI is huge. And so to me, that says we need to take advantage of what the AI devices are and the AI software and tools ecosystem is providing. You, as people who write, develop new algorithms and pay attention to floating point arithmetic, developing new algorithms that can take advantage of these devices. So things that take advantage of lower precision arithmetic, for example, would be a good opportunity. Using AI inference engines as complement or a replacement for analytic models is another opportunity. And then last is just leveraging all these AI tools, the generative AI tools, things like Copilot, ChatGPT, and other similar tools. These are tremendous productivity enhancements to the community. Okay, summary. The Exascale project, we explored a lot of approaches to performance portable accelerator-based computing. We focused on very high end, but most of the innovations were on the node and are suitable for anybody who has an accelerator. We did risk this path. I mentioned the El Capitan, climbing, de-risking. It's very similar here. We've provided a lot of new tools that you can use, things like Cocos, ZFP, Spack are a few. E4S provides many more, and you can have ready access to those. And HPSF is a bright, shining new organizational structure to this. Peso and CAS and the other SSOs are evolving to meet future needs. I'm happy to talk in the future. Here's an email address you can reach me at. Okay, and then the last comment. So DOE has learned a lot about producing software. We learned how to do that in a big way, and hopefully that will inform future efforts. We hope for a big AI for science initiative, and that a lot of what we learned in ECP can be carried forward. We propose to continue and expand in all the ways I just described. And we want to realize the potential of the ECP legacy in this exascale era as we go forward. And then lastly, we want to work with the HPC community, including people like you who are interested in this topic and want to engage. And last thing, thank you. And I'll stop here.
Thank you. Thank you, Mike, for a very nice talk. And yes, it's hard to clap for a virtual talk. But I do want to open it up for questions now. I want to answer one question that's already was asked. Yes, this is being recorded, and will eventually be posted on various websites, IM website, as well as on our YouTube channel for our activity group. But going to the other questions, and for the rest of you, please post more questions into the Q&A section. We have still over 90 people here. We had more than 100 attendants during the height of the talk, so I just want to say that. So the first question here was, does Cocos achieve the same level of performance compared to using native tools?
Yeah, that's a great question. The answer is sometimes yes, sometimes no. And it's still very useful, even in situations where it doesn't always achieve the same performance. Sometimes it can even be faster. You know, these are kind of cat and mouse type games, right? That as people learn new approaches to express algorithms or tweak algorithms, you know, one team will learn it and then their code will be faster, and the other team learns it and then their code is faster again. But I think that and I didn't get into this detail in my talk, but the key thing is Cocos provides you with out of the box a compilable version of the code for the target device, whatever it is, right? If a specific flavor of GPU, the next release of a GPU, the next release of the software stack for an existing GPU, or ARM CPUs with vectorization. It provides you with a ready-made build that already runs and takes advantage of the high performance features of that target architecture, that target device. Now, in some, for some kernels it may be fast, as fast as you need, as fast as it can be, and you're fine. In other cases, it might not be as fast as you need, but it's not one of the items that shows up high in your performance profile. And so you're okay with that. And then in some instances, it might be a little slow, and so slow enough that you want to have a custom implementation of that. And that's okay, because you can write a custom implementation of the most performance sensitive kernels and still leave the rest of your code as Cocos expressions. And then you have just this tiny amount of code divergence where you have specialized versions for different devices. Also, by the way, you also have the Cocos version that you can use for correctness verification. Did I write this hand-coded code well enough, so that it's running correctly? And so the nice thing about, and again, Raja is like this as well. I'm saying Cocos because it's something I know well, and we talked about it here today. But the notion of using these compile time polymorphic approaches is how you get a nice blend of productivity. And we can't, with codes that have lots of parallel loops, it's just simply too hard, I think, to write a customized version of every single loop set in a large code. And so this is a way of providing, a nice blend of a generality and the ability to customize where needed.
Okay, thank you. Another question is, well, this is also still Cocos related. Does Cocos require modifying the kernel? So,
Does it require, say it again, please?
does Cocos require modifying the kernel?
Not sure which kernel.
Yeah, I'm wondering if they just...
If it's the OS kernel, it does not. It's all in user space. If it's the kernel, the loop body, there are two ways to do it. You can use what's called a lambda expression, by which you insert the expression. The little example I showed of an AXP, that uses the lambda expression, which essentially is the loop body, and it can be more than one line. I just had a simple one line. But if you have a more elaborate kernel, meaning the loop body is larger, you can use what's called functor syntax, which simply means that you overload the paren operator in using C++ syntax. And then you can express the kernel as this functor, which sits aside as a separate C++ function. So I don't know if I answered the question or not. Hopefully I did.
Yeah, it's kind of hard to say, so,
Yeah.
but and then another question was, does Cocos support cache blocking for CPUs?
Cache blocking for CPUs, meaning I'm guessing in the so it supports multiple execution patterns that implicitly support cache blocking. So in that way it does. Again, if you need to get to that level of optimization where you're, tuning for the cache specifically, I'm not sure if they're talking about the streaming multipart processor cache, because every little streaming multiprocessor also has its own little cache. But then there's also these larger caches. There's also texture memory, which if you're doing, sparse gather of data, like for a sparse matrix vector multiplication, you stream data from main memory on the GPU through the texture memory, because the texture memory serves as a read-only cache of that data. And all of those things are possible to do with Cocos. And again, to realize maybe not the complete optimized approach, but a pretty good one. And then if you need something more specialized than that, then you can write the hand-tuned code for that version.
Okay, so there are lots of questions now. Could
Mhm.
you say a few words on your take on the importance of emerging high-performance, high-productivity programming languages like Julia and Chapel as they relate to the future of HPC and exascale computing?
Yeah, sure. So yeah, I track those languages quite a bit. Julia, I think, has emerged and is, I think, it's reaching a critical mass, or maybe it's reached it already, of kind of a user base, market base, where I think it has legs. Chapel, I have known truly since more than 20 years. I've known about Chapel. I've written some programs in Chapel more than 20 years ago. I understand that there's a renewed effort around Chapel, and that it has a kind of a fresh momentum going forward. It's hard for me to say if it's going to succeed. I think in all of these cases, it's not so much about the technology or the beauty of the expression. Yes, it has to be a really good programming system and address user needs. The key thing is, does it have market share? Does it have a sufficient market base that will sustain it going forward? And a lot of the really good technical ideas never gain traction enough because they don't have a market. And that's the real challenge. There's another, Rust is another language that's often being used to replace C, that provides memory safety. And as there are more mandates coming down from our sponsors about software security, programming languages like Rust come with a better built-in guarantee of software security, simply because the memory is managed. C++, you can do all sorts of really, really risky things, but you can also put in memory safety by using certain types of data or pointers, smart pointers and things like that, that force the release of memory, manage overflow data, access, overflow of arrays and things like that. And so there are lots of new languages that are coming out, lots of new capabilities. That I try to track myself. Again, I look to market share as to whether or not something is going to make an impact.
Okay. Can you elaborate a bit more on how the low precision calculations of AI workloads can be leveraged for the high precision needs for scientific application?
I will put that question back to you, because I think this is exactly the community that can do that analysis and make use of low precision arithmetic. Did you know that on Blackwell they have a 4-bit data type? Can you imagine that? I mean, that's like I don't know, a sign bit and a little bit of an exponent and just a hint of what direction the value goes. It's just amazing. Now, I don't know that we can use FP4 in our work. But I think there's a chance to use FP16 or bfloat 16, which has a nicer accumulator there to protect against overflow for accumulations and things like that. So really, I put it back to you. There's quite a bit of literature in this space. ECP invested a lot in mixed and multi-precision. So if you look, Ulrich has been involved in some of that. Hartwig Onst led the effort coordinated the effort for ECP. There's a lot of good reports out there, from the Exascale project. You can go to exascaleproject.org and find those reports. Also, there's just lots of literature. But it is an opportunity, right? I think for us as a community, we've all become accustomed to 64-bit floating point. And it was 30 years ago, 32-bit floating point was commonly used because that's what workstations had, and they didn't have hardware support for 64. And then we got comfortable with 64, and we've been using it ever since. But do we really need it everywhere we do computation? Certain phases, yes, absolutely. If you're doing orthogonalization, you want every bit possible in that mantissa in order to remain relevant, right? But outside of that, what do you really need it? I don't know. That's our job, right? As numerical mathematicians, to do that kind of work.
Yeah. So there's another question along this line. How much focus is on accuracy and reproducibility when developing this kind of universal infrastructure that works across many different machines?
Yeah, that's a good question. Bitwise reproducibility essentially goes out the window, at least when it comes to doing production runs. Some of the libraries will support, a reproducible summation capability in debug mode. But generally speaking, if you want that kind of bitwise reproducibility, the performance loss by doing that is so high that you really can't tolerate it in most instances, except for debugging. At the same time, what I think we need to do is couch those variabilities of floating point arithmetic in a larger context where you can do, verification, say synthetic problems, for example, where you know what the results should be and you can compute, that even in the presence of those variations with some confidence that you're getting the right answer, or in a validation setting where you have an external approach that you're comparing your answers to. And so it does get away from this notion of having like a gold standard file where you do a diff of your produced testing results against the known trusted data or set of output. That approach, I think we have to move away from it with any kind of concurrent execution because of the details of what we try to do. There are variations of floating point arithmetic where you essentially chop off those last bits in the mantissa to eliminate that variability. There's been some nice work done by Jim Demmel and others over the years. But that's a special data type. A lot of the libraries, Cocos, for example, can take a scalar type that you define. It doesn't have to be the native types. You can define your own data type, and you could put in that data type, for example, as a way. But yeah, that's a challenge, but it's a challenge for anybody who wants to be on the new performance curves for computing systems.
Okay, let's see. There's one question. What about legacy Fortran code? Is there any experience on how to make this more portable with regard to different architectures, or does this require writing wrappers to Cocos and/or eventually rewriting large parts of the code? I know you mentioned.
Yeah, there are a lot of specifics that person would. I can try to talk about kind of general principles about that. A lot of the details of your code matter a lot. So what are some general principles? There are already Fortran wrappers to Cocos that you can call. They are developed out of Los Alamos. And I think by now they're pretty robust. I have not used them, so I can't say, but it is such a strong need that some people have invested in developing them and providing them to the broader community. So yes, you can certainly call Cocos from Fortran through wrappers that you didn't have to write yourself. So that's a possibility. The bigger aspect of this, and this was in one of my early slides, is that if you want to take full advantage of modern GPUs, so much of the bandwidth and compute capability of a node is in the GPU device itself. The CPU is there just basically to try to stay out of the way of what's going on. It's just orchestrating the processes and trying to just stay, get out of the way so you don't slow things down. And that is really hard to do by trying to start with a pretty vanilla MPI code that is unaware of GPUs at all. And it requires a significant effort. And first of all, just understanding how would you want to, a code like that to behave, and then refactoring it if that's what you want to do, taking the code and transforming it, and then trying to get it to a state where you have pushed all that computation onto the device and to get the most performance out of it. And that part where you have to get all of it over there, that's the part where you probably have to wonder, is it makes sense to stay with Fortran? Or if I'm going to be doing this refactoring, why don't I pick another language, that is more amenable to it? And you can pick C++. Within ECP, we had a lot of code teams. Now we had, relatively speaking, had a fair bit of funding, so code teams could do this and time and could succeed in doing it. Not everybody has that. In fact, a lot of people don't have that kind of luxury of being able to refactor and by putting in a new language. But that might be your best answer. Maybe you accrue funds, over a span of time, so you can put in that intense effort to do the refactoring. And C++ is a great language for that. If your track language is another one that's interesting is Mojo, which is Chris Latner's new language. It has a lot of really cool features. It's Python compatible, but it does compile compilation to native data types. It also supports low precision data types. So it's a really interesting development in this space.
So, yes, we are running almost out of time. There are more questions here, like maybe one short one. Can Cocos address RISC-V architectures?
Sure. Yeah, it can. I don't know how far along they are in optimizing for that. I just don't know. I haven't been briefed on, the Art RISC-V stuff lately. But I know we have a lot of European users. RISC-V is an important target architecture for the European HPC community. So somebody's working on that, and I just don't know the status of it.
Yeah, and one more complete. What modification would be required to the tool chain presented if we want to target an HPC that has a cluster of FPGAs in addition to CPUs and GPUs?
Yeah, that's a great
can be used?
question. Yeah. Okay. So we are able to handle heterogeneous nodes. We know how to handle them because we handle GPUs. No, and we handle not just NVIDIA GPUs, but NVIDIA, AMD, and Intel. And so in a certain way, we have I would say software ecosystem portability across multiple heterogeneous device types. So we know how to handle compilation, special compilation for all three of those and pass it through our ecosystem to build an application. We know how to get the ISA, and execute on those devices, launch on those devices. So in a way, we're there in a demonstrable way because we're supporting multiple GPUs. Now you can argue that an FPGA is yet just one more, of those devices. And so in that sense, we're pretty well prepared. But now, are we all the way? I can't say that. We haven't had enough experience really compiling in a repeatable fashion with FPGAs. And so I'm sure there's more work to do in that space. But again, because we've done this for other heterogeneous devices, the question you'd want to ask is, well, what would it take to introduce the ability to compile for FPGAs into the ecosystem we have rather than live outside of the ecosystem? There are other things that are coming along too. As I mentioned, there are data flow devices that are really impressive, and especially for sparse problems. And you'd want to be able to compile for those as well and execute key pieces. Quantum is the same, right? Quantum, from an HPC perspective, is a specialized compute device. It's got to have a host. And so that's another example of where I think we have the right architecture in place. We have demonstration of multiple GPUs, but there's still for sure a lot of work to support all those.
Oh, thank you. I think we should end at this point because we are almost into a whole hour and you answered 10 questions. So,
Sure.
Thank you very much. This was a very nice presentation, and I really appreciate you taking the time to giving this talk and answering all these questions. So
Yeah, my pleasure. It's been a lot of fun.